Hello students. Today we're gonna solve one problem which is shared from one of my students from Carnegie Mellon University, and he was saying that he's having trouble working on these problems. So yes, I think so. This could be a problem for almost everyone at the beginning when you start learning organic chemistry or Auger 1 particularly. So this particular molecule is a Ramelteon, and they're asking in A, what is the molecular formula of this particular compound? So I've already numbered the carbon skeleton here. Of course, this numbering is not as per the IPAC standards or something. This is just to make sure you understand that all the carbons are numbered. So in total, we have 16 carbons over here. We have total 16 carbons. So if you look at the molecular formula, I can simply say it is C16. Number of hydrogens would be 3, CH2 2, so 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So total 21 hydrogens. There is one nitrogen, and there are two oxygens, so to say. Now note that when you are writing a molecular formula, you always, this is a convention. It's not a rule or something, but it is a convention that we write carbon first, then hydrogen, then any heteroatom, nitrogen, halogens, or anything, and at the end we write the oxygen. Okay, next question. How many sp3 hybridized carbon atoms are present in this particular structure? So let's look at, I've already created one structure, and we can actually circle the sp3 hybridized carbon. sp3 hybridized carbon is the one which is forming only single bonds. So this particular carbon is sp3 hybridized, because it's also forming only single bonds. Look at this particular carbon, a carbon which is attached to oxygen with a double bond. That's not sp3 because it's forming a double bond. Double bond means it's a sp2 hybridized carbon. Here, the CH2 carbon is sp3. This is also sp3. This is also sp3, sp3, and sp3. Rest of the benzene ring over here has all 6 sp2 hybridized carbons. But there is one more, sp2, sorry, sp3 and sp3. So all the sp3 carbons are specifically circled here. How do we determine what is sp3 hybridized carbon? The carbon that is not double bonded or triple bonded, we can consider that as sp3 hybridized carbon. Remember, of course, the carbon should not have any charge, negative or positive, because that will change the entire scenario. So there are in total, I'll just write it down here. So there are total 9 sp3 hybridized carbon. 1, 2, 3, 4, 5, 6, 7, 8, 9. So that total 9 sp3 hybridized carbons. Okay. Next question: how many sp2 hybridized carbons are present in this structure? Okay. I'll duplicate this structure, and now we have to determine sp2 hybridized carbon. sp2 hybridized carbon will indicate it with a box. So sp2 hybridized carbons are the carbon will be the carbons which forms a double bond in a structure. Carbocations and carbanions is altogether different story. We are not discussing that. We are talking about in this structure where the double bonded carbons are going to be sp2. So mainly in sp2 hybridized carbon, the p orbitals are combined together to form a pi bond, and that's why it leads to sp2 hybridized carbon. So 1, 2, 3, 4, 5, 6, and 7. So total 7 sp3 hybridized carbons again. I'll just write it down here. there are 7 sp2, sp2 hybridized carbons. How many sp hybridized carbons? Sp hybridized carbons are carbons which forms a triple bond. So we don't have any triple bonded carbon here. So definitely there is no sp hybridized carbon. So I'll say 0 sp hybridized carbon. How many lone pairs are present in the structure? Okay, every heteroatom will have a lone pair. Heteroatoms are atoms other than carbon and hydrogen. So oxygen has 2 lone pairs, nitrogen has 1 lone pair, halogens will have 3 lone pairs, sulfur will have 2 lone pairs. It's easy to determine the lone pairs here. So look at the oxygen. Oxygen being, if you look at the oxygen's position in periodic table, if I show, oxygen is from 16th group or 6th A, so there are 6 valency electrons, and that's why it forms 2 bonds, and uh, uh, 2 electrons are used to form a bond, and rest of the 4 electrons or 2 pair of electrons remains as it is as a lone pair. So we can expect 2 lone pairs on the oxygen. So let me draw those 2 lone pairs on oxygen here. So this would be 2 lone pairs on oxygen. There we go. This oxygen will also have 2 lone pairs, of course, because it's also forming 2 bonds. Remember, if the oxygen forms 3 bonds, then in that case it will have a positive charge and it will have only 1 lone pair. In only that case, oxygen can have only 1 lone pair, because one of the lone pair is utilized to form another bond or a third bond. For example, it's a hydronium ion, H3O plus, that would have 1 lone pair. But here, both oxygens are neutral, and that's why they will have two lone pairs each. The nitrogen would expect to have 1 lone pair. So let's put up the nitrogen with a lone pair here. And there are 1 lone pair. So there is only 1 lone pair on a nitrogen. So we have 2, 3, 4, 5. Total 5 lone pairs in this particular molecule. So we have 5 lone pairs. Identify each lone pair is localized or delocalized. Lone pair next to pi bond will always be delocalized by resonance, and the lone pairs on oxygen, particularly here, that is C double bond O oxygen lone pairs are localized. The oxygen lone pair here on this sp2 hybridized lone pair, sp3 hybridized oxygen, these lone pairs definitely are adjacent to C double bond C, and that's why they will be delocalized. So I can simply show the delocalization like this. You can show further delocalization as well. Then the nitrogen lone pairs are adjacent to a C double bond O, and that's why this lone pairs will also be delocalized. So there are 2 lone pairs which are delocalized. So this one is delocalized lone pair. I'll just write down that. And the nitrogen lone pair is also delocalized, whereas oxygen lone pair is specifically localized, not delocalized. Fantastic. Next question is identify the geometry of each atom. Okay, so all sp2 hybridized carbons will have trigonal planar geometry. All sp3 hybridized carbons will have a tetrahedral geometry, and sp2 carbons will have trigonal planar geometry. Okay, then the nitrogen, if you look at the oxygen, this particular oxygen will not have any geometry as such. You can simply say linear because there is only one bond there. But this oxygen, which is actually uh, expecting us to have a lone pair that is delocalized over the pi bond. the oxygen atom will delocalize that lone pair. But note that the lone pairs, there are two lone pairs which are not taking part in any bonding. So you would expect the oxygen to to have a bent geometry. It will have a bent geometry. So this is delocalized and I'll say a bent geometry over there. This oxygen is linear, rest of sp3 tetrahedral, sp2 trigonal planar, and the nitrogen particularly. Nitrogen, as the lone pair is in delocalized manner, the nitrogen has a lone pair that is delocalized. So I would expect that to have this is delocalized and that to have a trigonal planar geometry. Because the lone pair is in conjugation with the C double bond C or C double bond O, I'm saying. Okay, and that's how these are the geometries of different atoms over here. Hope you like the answers, and if you have any questions, if you have any difficulties, please comment me in this video. I'll try my best to help you out on that. And if you're looking for organic chemistry tutoring sessions with me, please write down in the comment box, or maybe you can email me out, then we can fix the lesson. Or you can also visit my Hybrid profile. There you can actually book the lessons as per the availability. Thank you so much. We'll see you in the next lesson. Bye bye.